Today's activity is going to involve verifying the law of conservation of momentum. We're going to do this in a bit of a different way than you've ever done an activity before. Okay, we're going to measure an initial velocity, a final velocity of a two-cart collision. We're going to do that over several trials. We're going to plot a graph, and then we're going to use that graph to determine whether momentum was in fact conserved or not. But in order to get several different pieces of data, several different trials worth of data for the velocity of two different carts, we're going to use a bit of a unique way, a bit of a different way of measuring that data. We're going to use what's called a motion sensor, which is going to be attached to something that's called an air link, which is going to beam the data to your iPhones, which you're going to in turn email to yourself so that you can analyze it on Microsoft Excel or wherever it is that you want to analyze it. Let's talk about the activity first, and then we'll talk about exactly how we're going to use the iPhones to collect this data. So we want to measure, or we want to determine whether the law of conservation of momentum is valid. A problem is always in the form of a question. So we're going to phrase it like this. Is the law of conservation of momentum valid for the collision of two dynamics carts? Okay, simple as that. There will be three variables, as there always is. The control variable is always the easiest one, it seems, because it's the one that always has to be held constant. It's everything else, right? Everything else besides the manipulated variable and the responding variable. We're not going to go through those right now, but I will go through the manipulated and the responding variable for you. If you take a look up at the front here right now, you see these two carts that we're going to send moving. Cart number one is the silver one. Cart number two is the black one. Trial number one might look something like this. Cart one goes toward cart two, collides, sticks together, goes off as one object. Trial number two might look something like this. Same thing. Same thing as trial number one, at least almost. Trial number three might look something like this. Cart number one again goes forward and hits stationary cart number two. What did I change in all those different trials? No, yeah, the distance isn't so critical there, it's the speed. Right? It's the speed of cart number one. So the initial velocity, What changed in response to that? What changed because of the initial velocity? I'm sorry? Well, it would, but that's not directly. If the initial speed is different, then what else is going to be different? The final speed, the final velocity, right? So your manipulated variable would be the initial velocity. Your responding variable will be the final velocity. Now, you saw real quickly up here a really short demonstration of these two carts colliding. This is kind of a blown-up version of what the apparatus is going to look like. You can see, first of all, here a triple beam balance scale. That's going to be used to measure the mass of cart number one and of cart number two. Okay, so we need the mass in kilograms of both cart number one and cart number two. Now, there's also a track that's underneath both of these carts. This track has little grooves in it that allows cart number one to roll along it really nicely and not go off the track. It also provides us with the opportunity to attach this thing that we call a motion sensor. This motion sensor is connected by a wire to a device right here that we call an air link. Holding it up right now, it looks something like this. This air link is going to be paired via Bluetooth to your iPhone. So the data is not going to appear anywhere in this air link or this motion sensor. The motion data for both of these carts is going to appear directly in real time as a graph on your iPhone. Now that graph, you're not going to do anything with that graph. You're going to actually email the data to yourself so that you can plot a better graph on Microsoft Excel. That make sense? So you do one trial, you send cart number one down towards cart number two at a certain velocity. It's going to hit and collide with cart number two. It's going to stick together because you get two pieces of sticky tack, one right here and one right here. They stick together and go off as one object. You're going to measure V1 and you're going to measure, VI I should say, and you're going to measure VF. Then you're going to repeat that experiment with a different initial velocity. Then you're going to do it again and again and again and again. Now, it doesn't matter if you go in order. If you find that, you've got 7 trials and it's like, well, I can't go any faster. This thing's going to go right off the track. Well, then slow down. It doesn't have to be in order. Just go 8 or 9 or 10 different trials of different initial velocities. By the way, a blown-up version of this motion sensor appears right here. There's a little setting on it where you can flip that switch to this little setting or to this setting. You want to be on this one. Okay, that's used to measure the position, velocity, and acceleration of something small and nearby, like a dynamics cart that you see there. If you have it on the other one, it's used to measure the position, velocity, and acceleration of an object that's big and far away, like a person walking across the room. Okay, we're not measuring the velocity of the person, we're measuring the velocity of a dynamics cart. All right, so what's the graph going to look like on your iPhone once you collect the data? For each trial, you'll get something that looks something like this. There's 3 little different things here. There's this section, and then there's this section. These 2 sections appear to be pretty close to straight lines. This section is also a straight line, but it's horizontal. Can you tell me what's happening in that first section there, that horizontal straight line? It stands still, right? It hasn't moved yet. Okay, so I started the timer before I pushed it. That's okay. When you email the data to yourself, just delete that data. Or in the end, don't delete it, whatever. Just don't use it in your analysis. What does this stand for? This line is a straight line at a fairly steep slope. What does it mean? Yeah, the slope of that graph will be the initial velocity. The slope of this one will be the final velocity. So you're going to get for each of these trials a VI and a VF. And then you're going to put that data along with the measurements for mass that you've already taken into this table that looks something like this. 8, 9, 10 different trials for initial velocity, 8, 9, 10 different trials for final velocity. Okay, so far so good. A little bit of work here because we've got to email 10 sets of data to yourself, although you can do that all at once. You don't have to do it after every trial. You can wait till you're done and then email everything together. From each of those graphs, get the initial and the final velocity. And then, what are you going to do with the data table? What do we always do with the data table? Graphing. We're going to plot a graph. That graph is going to be VF versus VI. The first column of a data table is always the manipulated variable. The second column is always the responding variable. That first column, or that manipulated variable, always goes on the x-axis, and that second column, or the responding variable, always goes on the y-axis. This graph will be a straight line. What are we going to do with this graph? Well, the first thing we need to do is identify an equation that represents it. An equation that represents any straight line graph, back in Math 9, is y is equal to mx plus b. You guys remember that, right? No? Really? Well, trust me, that equation describes the equation for any straight line graph, whether it's d versus t or vf versus vi. Y equals mx plus b. Now, the y-axis is vf. M stands for what? M stands for slope. Good. So the y-axis, vf, is equal to the slope times the x-axis, v1i. Now, b is the y-intercept, okay, where it goes through the y-axis, and that should be at the origin, so we can cross that off. Okay, there is no y-intercept. It's effectively 0. So there's an equation that describes this graph, a general form of it, y equals mx plus b, and then a specific form specific to this particular graph and this particular experimental setup. Now we're going to make an assumption. We're trying to test the law of conservation of momentum. We're going to assume for a minute that it's true, that it does hold. If it does, then the initial momentum of object number 1 plus the initial momentum of object number 2, which is 0, will equal to the final momentum of both of the objects combined, m1 plus m2 times vf. Now what we want to do is take this equation and rearrange it to take the same form as this equation. So what we're going to do is take the m1 plus m2 over to the left side by dividing. It becomes m1 over m1 plus m2. I'm dividing by m1 plus m2 times v1i. Some of you might write it as m1 v1i over m1 plus m2. I chose to write it as m1 over m1 plus m2 times vi. Doesn't really matter, it's the same thing. Now, this is not the hardest part of this, but it's the crux of it here. I'm going to cross off things that appear in my graph equation, vf is equal to the slope times vi, and that appear in my pi equals pf equation. So cross off things that appear in both. vf appears in both. vi appears in both. Well, we can't cross off the slope because it doesn't appear in both. We can't cross off m1 plus m2 because it doesn't appear in both. What have we just learned? The slope of this graph is m1 over m1 plus m2. Physics 20, you guys learned that position time graphs give you a slope equal to velocity. How do you know that? Because your teacher told you that the slope of a position time graph was velocity. How do you know that the slope of a velocity time graph is acceleration? Because your teacher told you. Well, how did your teacher figure it out? How does your teacher know that a velocity time graph gives us acceleration? How do we know what the slope of any graph represents? Well, we can go through an analysis like this to determine what the slope represents. This is a more confusing slope, m1 over m1 plus m2, but we go through the exact same analysis to figure this out as we do the slope of a v versus t graph, the acceleration. All right, next I want you to calculate m2 and compare it with the measured value of m2. Why do we want to compare it with the measured value, the one that you took with the triple beam balance scale? Well, because we made an assumption here to get the value of m2, to calculate the value of m2. We assumed that the law of conservation of momentum holds. If we find that the value that we calculated for m2, making that assumption, matches up with the measure that the value that we actually measured for m2, then the assumption that we made must be correct. The assumption of pi equals pf must be correct. Here we're assuming it to be correct to do the analysis of the slope is equal to m1 over m1 plus m2. But if m2 equals what it was measured to be, then that assumption must be correct. And the law of conservation of momentum is verified. Does that make sense? All right. Well, what if it doesn't exactly equal? Like, what's close enough? Let's calculate a percent difference. Percent difference is the actual minus the theoretical value over the theoretical value times 100. Somebody in the last class said that in French chemistry, they learned it was theoretical minus actual over theoretical. Is anybody else in French chemistry? You guys learned it like theoretical minus actual? No? Okay, well, it doesn't really matter, right? As long as you're not changing the denominator theoretical. Okay, whether you go actual minus theoretical or theoretical minus actual, you're taking the absolute value of it, so you're going to get the same number either way. If that percent difference is less than 10%, it's close enough. If it's more than 10%, then your conclusion would be, no, the law of conservation of momentum isn't valid. What else do we need? Your conclusion, was it verified? Either yes or no. How do you know? Yes, the law of conservation of momentum was verified. This is known because the value of m2 that was calculated was within 10% of the value of m2 that was measured. Or no, the law of conservation of momentum was not verified. This is known because the value of M2 that was calculated was not within 10% of the value that was measured. And then finally, we need our sources of error. List 2 or 3 different things that weren't great. 2 or 3 different things that could have been better. It could have to do with time management. It could have to do with technology. It could have to do with procedure, materials, apparatus, any of that stuff. Doesn't matter. And then list possible improvement that could make it better next time. All right? All right, let's get into our groups. We'll get our apparatus, and then I'll help you guys with pairing your iPhone with the AirLink apparatus.